So hello guys, welcome back to the channel. Welcome to Exile Island. Our goal and objective is to learn and master Python over the next 100 days. Today's day 75. So we'll be looking at this course called hypothesis testing in Python, where we'll be learning how to answer questions about our data set in a statistical rigorous way. So we'll learn to grow your Python analytics skills as you learn how and when to use common tests like t-test, proportion test, and square tests. So the first chapter talks about hypothesis fundamentals. So how does hypothesis testing work and what problems can it solve? To find out, we'll walk through the workflow. Sorry about that. So the first chapter talks about workflow for one sample proportion test. So in doing so, you encounter important concepts. We'll be covering something like this called p-values, false negative and false positive errors. So without further ado, let's get started. So the link to the data set used in this uh, lesson will be under the video description under hypothesis testing or further in Python. So without further ado, let's sorry about that. Let's get started on hypothesis testing. Okay, hold on a minute. Okay, let's create a new Python file for hypothesis testing in Python. You need Jupyter notebook rather. So we're connecting to our normal feather file for this. So let's learn what is called hypothesis testing in Python.
Hi, I'm James. Welcome to this course on hypothesis testing in Python. To start, let's look at a real-world example where a hypothesis test was crucial in a decision-making process. In 2013, Electronic Arts, or EA, launched a video game called SimCity 5. Leading up to its release, they wanted to increase pre-order sales. They used an experimental design technique called A/B testing, which has roots in hypothesis testing, to test different advertising scenarios and see which improved sales the most. Website visitors were split into a control group and a treatment group. Each group saw a different version of the game's pre-order sales page. Here's each version of the SimCity 5 pre-order page. The control group saw the version with a banner advertising money off their next purchase with each pre-order. The treatment group saw the version without the banner. EA compared the percentage of checkouts for the two groups to see which performed best. Our naive guess would be that the advertisement increased pre-order sales. The results of the A/B test were surprising. The treatment page without the advertisement resulted in 43% higher sales than the control page with the advert. The experiment proved that our intuition that more discount adverts would result in more sales was false. We might ask ourselves, was the 43% difference a meaningful difference between the control and treatment groups, or was it just random chance? To get this answer, we'd need the original dataset from EA, which isn't publicly available. However, the method to answering this question of significance would involve techniques from both the Sampling in Python course and from this course. Each year, Stack Overflow surveys its users, who are primarily software developers, about themselves, how they use Stack Overflow, their work, and the development tools they use. In this course, we'll look at a subset of the survey responses from users who identified as data scientists. Let's hypothesize that the mean annual compensation of the population of data scientists is $110,000. We can initially examine the mean annual compensation from the sample survey data. Annual compensation, converted to dollars, is stored in the converted comp column. The sample mean is a type of point estimate, which is another name for a summary statistic. We can calculate it with pandas using the dot-mean method on the converted comp series. The result is different from our hypothesis, but is it meaningfully different? To answer this, we need to generate a bootstrap distribution of sample means. This is done by resampling the dataset, calculating the sample mean for that resample, then repeating those steps to create a list of sample means. Here's a histogram of the bootstrap distribution. Its bell shape means that it's roughly normally distributed. Notice that 110,000 is on the left of the distribution. Recall that the standard deviation of the sample statistics in the bootstrap distribution estimates the standard error of the statistic. Since variables have arbitrary units and ranges, before we test our hypothesis, we need to standardize the values. A common way of standardizing values is to subtract the mean and divide by the standard deviation. For hypothesis testing, we use a variation where we take the sample statistic, subtract the hypothesized parameter value, and divide by the standard error. The result is called a z-score. Here are the values we calculated earlier. The sample mean annual compensation for data scientists of around $120,000 minus the hypothesized compensation of $110,000 divided by the standard error gives a z-score of 1.707. Is that a big or a small number? Determining that is the goal of this course. In particular, we can now state one of the uses of hypothesis testing, determining whether a sample statistic is close to or far away from an expected value. One final thing. Here's a plot of the probability density function for the standard normal distribution, which is a normal distribution with mean of 0 and standard deviation of 1. It's often called the z-distribution, and z-scores are related to this distribution. We'll encounter the z-distribution throughout this course. Time to begin.
Okay, let's understand the use of A/B testing. It says in this video, you saw how Electronic Arts use A/B testing on their website when launching SimCity 5. One version of the page showed an advertisement for a discount, and one version did not. Half of the users saw one version of the page, and the other half saw the second version of the page. What is the main reason to use A/B testing? Hmm. Hmm. So A/B testing lets you compare scenarios to see which best achieves some goal. So that's the use of A/B testing. So let's calculate the sample mean. So the late shipment data set contains supply chain data on the delivery medical supplies. Okay, we have the data set here. Let's give it a shot and see what the data set looks like. I'll just go to my local file and connect to the data set called late shipments. So it is a further file. I want to copy the parts. Just paste the parts here. Then I can just copy and paste it there. Okay, if I show on this code, that should show us what the data set actually looks like. Let's see what the late shipments data set looks like. Voila. Because we have over 1,000, just 1,000 rows of data and 27 columns about shipments data. Let's do dot edge to see just the first 5 rows. So this is what the data set looks like. We have the ID, the country, managed by few via vendor, and a whole bunch of other data points here. Okay, so let's continue. It says the late shipment data set contains supply chain data on the delivery of medical supplies. Each row represents one delivery of a part. The late column denotes whether or not the part was delivered late. The value of yes means that the part was delivered late, and the value of no means the part was delivered on time. You will begin your analysis by calculating a point estimate or some statistics, namely the proportion of late shipments. In Pandas, a values proportion is a categorical data frame column can be quickly calculated using syntax. For late shipments available at Pandas is late as PG. Let's put the late shipment data sets. Late shipment. If I say points, points, when my points returning, let's see what the late shipment data set will do. Data frame objects. Okay, same result here. We got that. To calculate the proportion of late shipment in the sample, that is the main cases where the late column is yes. Okay. The main cases where the late column is yes. Okay. That will be late shipments. Then the column that we want. What the late column, right? So we want the late column. Where's our late column here? Is our late column. Where the late column is either yes or no. Let me check my keyboard. Late column. Then dot the mean. Oh, we're having an error here. We're supposed to use one line of code. Oh, why am I getting error in my line of code? Oh, I've not specified the value I want. Where the latest column is equal to yes. Okay, now let's run the code. Yes is not defined. I'm having an error here. Let's see. Let's get up on the error also. Since it is a string, you have to wrap it in double quotes. Don't always forget that. I think the proportion of list statement is 76. Okay, let's see it here. Let's see 61%. Hmm. For probably 6.1, 6.1%. Let's see, which is 6.1% exactly. We'll calculate the proportion of list shipment in the sample is 6.1%. Okay, I can see that. Calculating a z-score. Since variables have arbitrary ranges and units, we need to standardize them. For example, hypothesis tests that gave different answers if the variable were in euros instead of United States, US dollars would be of little value. Standardization avoids that. One standardized value of interest is the hypothesis test. Hypothesis is called a z-score. To calculate it, you need the three numbers: the sample statistics, the hypothesized statistics, and the standard error of the statistics. The sample statistics are available as late prop sample. The late shipment, the distribution is a bootstrap distribution of the proportion of late shipment available as a list. Okay, lastly, hypothesize that the proportion of the late shipment is 6%. Okay, we need to hypothesize. Let's see that. Okay, so we need to do three things here. We need to hypothesize that the proportion of late shipments is 6%. Then calculate the standard error from the standard deviation of the bootstrap distribution. Calculate the z-score. Yeah, it's the 6%. We're not going to say 0.06. Sorry, since we calculated that, calculate the standard error. So how do you calculate standard error? Standard error will now be NPSTD so boot distribution DDOF minus 1. Okay. So standard error. Let's how we calculate the standard error. So standard error will be calculated as this for our late shipment boot distribution. Then we have that already. Find this score of late proportional sample. Now find is this score. That will be standardized value divided by hypothesis. Okay, let's do that. Voila, we have our results here. Let's see if it nailed it. Voila, we nailed it. That's how to do that. It can't work here because I don't have this standard error, this late shipment boot distribution, which is actually calculated from. I can do that. Let me start to calculate that standard error. Let's see how to do that. I should be able to do that in here. I should be able to generate a booster distribution. Let me do that with this sample here. Let's do that. We know we have the mean. Let's see. We know we have the mean of the sample, the mean proportion sample. We have it already here. So to calculate the bootstrap distribution, I should be able to do that. Let's see. Let's give it a shot. Now let's calculate the most bootstrap distribution. Let's see. Let's try to do that here. Mm. Ours is going to be late shipment boot distribution. So I calculate the late shipment boot distribution. It's going to be a list. I can do that 5,000 times. It's going to be late shipment boot distribution dot append calculate point estimate np dot mean. Mine is going to be this. It's going to be my late shipment in this instance. My late shipment in this instance dot sample converted. So it's going to be the late column. Let's see if this is going to make sense. Ooh, ooh. So let's get up on the error. Let's see if we can get up on the error. Let's get up on the error. Let's see if we can also calculate the late shipment boot distribution. Okay. Okay, we didn't get any error. Ooh. So we could not convert this string. Ooh. I only need the actual yes alone. for the yes. Let's see if we can solve this error real quick. So see if I can solve this late distribution calculation here. Okay, since I can't use convert because these are non-numeric value, I need to convert it to a mean. So let's use this method now. Let's see. Okay, so we have our late shipment distribution calculated already of yes, exactly. And voila, so that is all we got here. So we're able to calculate the mean proportion of yes. So I could just delete this one. Let's now see if our calculation we got the same results. Mean proportion of yes. Cancel the z-score here. What was the result we got here? 0.1333. We nailed it. See what we got here, 0.100. Still close though. So those are the calculation for the z-score, which is still pretty close. Interesting. The score is a standard measure of the difference between the sample statistics and the hypothesized statistics. Ah, voila, we're able to do that. Interesting. So let's learn all about p-values.
Hypothesis tests are like criminal trials. There are two possible true states. The defendant either committed the crime or didn't. There are also two possible outcomes, a guilty or not guilty verdict. The initial assumption is that the defendant is not guilty, and the prosecution team must present evidence beyond a reasonable doubt that the defendant committed the crime for a guilty verdict to be given. Let's return to the Stack Overflow survey. The age first code cut variable classifies when the user began programming. If they were 14 or older, they are classified as adult, otherwise child. Suppose previous research suggests that 35% of software developers programmed as children. This raises a question answerable with our dataset. Does our sample provide evidence that a greater proportion of data scientists started programming as children? Let's specify some definitions. A hypothesis is a statement about a population parameter. We don't know the true value of this population parameter. We can only make inferences about it from the data. Hypothesis tests compare two competing hypotheses. These two hypotheses are the null hypothesis, representing the existing idea, and the alternative hypothesis, representing a new idea that challenges the existing one. They are denoted H0 and HA respectively. Here, the null hypothesis is that the proportion of data scientists that started programming as children follows the research on software developers at 35%. The alternative hypothesis is that the percentage is greater than 35. Returning to our criminal trial comparison, the defendant can be either guilty or not guilty, and likewise, only one of the hypotheses can be true. Initially, the defendant is assumed to be not guilty, and similarly, we initially assume that the null hypothesis is true. This only changes if the sample provides enough evidence to reject it. Rather than saying we accept the alternative hypothesis, it is convention to refer to rejecting the null hypothesis, or failing to reject the null hypothesis. If the evidence is beyond a reasonable doubt that the defendant committed the crime, then a guilty verdict is given. The hypothesis testing equivalent of beyond a reasonable doubt is known as the significance level. More on this later in the chapter. The tails of a distribution are the left and right edges of its PDF. Hypothesis tests determine whether the sample statistics lie in the tails of the null distribution, which is the distribution of the statistic if the null hypothesis was true. There are three types of tests, and the phrasing of the alternative hypothesis determines which type we should use. If we are checking for a difference compared to a hypothesized value, we look for extreme values in either tail and perform a two-tailed test. If the alternative hypothesis uses language like less or fewer, we perform a left-tailed test. Words like greater or exceeds correspond to a right-tailed test. For the Stack Overflow hypothesis test, we need a right-tailed test, since we are looking for extreme values in the right tail. P-values measure the strength of support for the null hypothesis, or in other words, they measure the probability of obtaining a result assuming the null hypothesis is true. Large p-values mean our statistic is producing a result that is likely not in a tail of our null distribution, and chance could be a good explanation for the result. Small p-values mean our statistic is producing a result likely in the tail of our null distribution. Because p-values are probabilities, they are always between 0 and 1. To calculate the p-value, we must first calculate the z-score. We calculate the sample statistic, in this case, the proportion of data scientists who started programming as children. The hypothesized value from the null hypothesis is 35%. We get the standard error from the standard deviation of the bootstrap distribution. And the z-score is the difference between the proportions, divided by the standard error. We pass the z-score to the standard normal CDF, norm.cdf, from scipy.stats, with the default values of mean 0 and standard deviation of 1. As we're performing a right-tail test, not a left-tail test, the p-value is calculated by taking 1 minus the norm.cdf result. The p-value is 3 out of 100,000. Go calculate some p-values.
So let's calculate some p-values. So in this video, you saw how hypothesis testing follows a smaller process to criminal trials. If the following correctly matches up a criminal trial with properties of a hypothesis test. I'm just reading it real quick. Hypothesis analysis. No, so it's just a defendant is only assumed guilty, not hypothesis to be true. I pronounce you not guilty. Sometimes helpful to think of the hypothesis test as being a trial of statistics. Okay. I hope you got that. Let me go to that place again. So just as defendant is initially assumed not guilty, the null hypothesis is first assumed to be true. So that is the following matches the criminal trial with properties of hypothesis tests. Interesting. So left tail, right tail, two tails. Determine an appropriate type of hypothesis test for answering these questions. The hypothesis tests are used to determine whether the sample statistic lies in tails of the null distribution. However, the way that the alternative hypothesis is praised affects which tails we are interested in. Oh, we're not to do anything right tail, right tail, or two tails. Let's see. Difference between voting preferences of 40 years old and 80 years old. Ooh, that's that's funny. Says, should we expect Slack and Zoom to have the similar mean numbers of employees over the last 3 years? Hmm. He said, are grapes lower in popularity than raisins on average? On average, do cats tend to live longer than dogs? Ooh, dogs do live longer than. Let's go for right tail there. The hamburgers have more calories than hot dog. And let's put this in. Oh, we messed this up. Yeah. This is supposed to be. So this one is two tails. So our grapes lower is evidence of that Belgian workers have lower salary than Italian workers. We can't say yes. Those are two tails because the different alternate difference from now. So the hamburgers have more calories than hot dogs on average is right tails. The alternative is greater than the no. Interesting. So the tail of description that are relevant depend on whether the alternative hypothesis refers to greater than or less than difference or the difference between. Okay. Okay. Calculating p-values. Let's calculate p-values in this instance. So what type of test should be used for this alternative hypothesis? Okay. Mm. We two tailed or right tailed says in order to determine whether it to choose the null hypothesis or the alternative hypothesis, you need to calculate p-value from the z-score. Okay. So with the z-score, we will now return to the late shipment dataset and the proportion of late shipment. The alternative hypothesis is that the proportion of late shipment is greater than 6%. Okay. Now let's do that in Python. Let's see. Let's do this in here and see. So we have our late prop sample and standard error. Okay, so our z-score is 1, our p-value is 0.8413. Interesting. So with that information, what should be our answer? So we're going to use definitely a one tail. I said it was right tailed already. So right tailed is the best answer. So let's calculate this score of lead prop sample, calculate p-value of lead score sample using a right tail test. Calculate the z-score. Let's calculate the z-score. This is not what we were given. The z-score should be this, and the p-value because I was z-score here. 0.8413. So 0. Oh, this showing me 0.44. Oh, probably because I'm using some error here. Perfect p-value. The p-value is calculated by transforming the z-score with the standard normal cumulative distribution function. Okay. Okay, now let's look at statistical significance. That should be the last lesson here for this chapter.
Last time, we introduced p-values. P-values quantify how much evidence there is for the null hypothesis. Large p-values indicate a lack of evidence for the alternative hypothesis, sticking with the assumed null hypothesis instead. Small p-values make us doubt this original assumption in favour of the alternative hypothesis. What defines the cutoff point between a small p-value and a large one? The cutoff point is known as the significance level and is denoted alpha. The appropriate significance level depends on the dataset and the discipline worked in. 5% is the most common choice, but 10% and 1% are also popular. The significance level gives us a decision process for which hypothesis to support. If the p-value is less than or equal to alpha, we reject the null hypothesis. Otherwise, we fail to reject it. It's important that we decide what the appropriate significance level should be before we run our test. Otherwise, there is a temptation to decide on a significance level that lets us choose the hypothesis we want. The workflow starts with setting the significance level, in this case, 0.05. Next, we calculate the sample mean and assign the hypothesized mean. For the z-score, we also need the standard error, which we obtain from the bootstrap distribution. Then we calculate the z-score using the sample mean, hypothesized mean, and standard error, and use the standard normal CDF to get the p-value. In this case, the p-value of 3 times 10 to the minus 5 is less than or equal to 0.05, so we reject the null hypothesis. We have strong evidence for the alternative hypothesis that the proportion of data scientists that started programming as children is greater than 35%. To get a sense of the potential values of the population parameter, it's common to choose a confidence interval level of 1 minus the significance level. For a significance level of 0.05, we'd use a 95% confidence interval. Here's the calculation using the quantile method. The interval provides a range of plausible values for the population proportion of data scientists that programmed as children. Returning to the criminal trial analogy, there are 2 possible truth states and 2 possible test outcomes, amounting to 4 combinations. 2 of these indicate that the verdict was correct. If the defendant didn't commit the crime, but the verdict was guilty, they are wrongfully convicted. If the defendant committed the crime, but the verdict was not guilty, they got away with it. These are both errors in justice. Similarly, for hypothesis testing, there are 2 ways to get it right and 2 types of error. If we support the alternative hypothesis when the null hypothesis was correct, we made a false positive error. If we support the null hypothesis when the alternative hypothesis was correct, we made a false negative error. These errors are sometimes known as type 1 and type 2 errors, respectively. In the case of data scientists coding as children, if we had a p-value less than or equal to the significance level and rejected the null hypothesis, it's possible we made a false positive error. Although we thought data scientists started coding as children at a higher rate, it may not be true in the whole population. Conversely, if the p-value is greater than the significance level and we failed to reject the null hypothesis, it's possible we made a false negative error. Let's do some significant exercises.
Okay, so let's calculate some p-values further. Calculating types of confidence interval level. So if p-values denote here as p is the measure of the amount of evidence to reject null hypothesis or not. By comparing p-values to the significance level, you can make a decision about which hypothesis to support. Which of the following is correct conclusion from decision for significance level alpha or okay. Okay, so which of the following is the correct conclusion from the decision rule for a significance level? This one is denoted as significance level. Interesting. So if p-value is less than or greater than, you reject. If p-value is greater than, okay. So what's the possible answer here? I accept or reject. So let's say if the p-value is less than or equal to the significance level, you reject hypothesis A, alternative hypothesis. If p-value is greater than or equal to the significance level, reject the hypothesis, reject the alternative hypothesis, or if the p-value reject the so the p-value is greater than or equal to less than or equal to significant level, don't reject the null hypothesis. Ooh, I didn't get that. Likely decision making. If the p-value is less than or equal to the significance level, you reject the null hypothesis. Okay, so we know that right now. So finally, say we should calculate a confidence level. You can calculate confidence interval from least members are using the contour method, labeling lower and upper intervals. What is the contour method? Calculate the 95 significance level. Just say least shipment booster distribution equals to, for lower, that should be lower should be 0.025, which will be 25%. I'm going to use the contour method. That's NP dot contour least shipment booster distribution 0.025, which is 25%. And upper should be lead bootstrap distribution followed by that. So let's run the code. We should have our results by now. Let's give it a shot here also and see what we have. We see our bootstrap distribution here from the above here that we calculated here. Where is the late bootstrap distribution? So it should give us our results. So we have the same results here. Okay. That says, does the confidence interval match up with the conclusion to stick with the original assumption that 6% is a reasonable value for unknown population parameter? You say there's no relationship between confidence intervals and hypothesis tests. That may not be true. So since 0.6 is included in the 95% confidence interval level, we fail to reject null hypothesis due to a larger p-value than the results. Okay. So when you have a confidence interval with equal to 1 minus the significance level, if the hypothesized population parameter is within the confidence interval, you should fail to reject the null hypothesis. Okay. Type 1 and type 2 errors. Oh, let's differentiate between type 1 and type 2 errors for now. False possible type 1 errors. Rejecting the null hypothesis when in fact the null hypothesis is false. Hmm. So false possible type 1 error, there's false negative type 2 errors. Okay. Okay. Find the defendant guilty when in fact the defendant did not commit the crime. Hmm. Okay. And they were innocent. That should be an error, definitely an error. Let's look at it again. Some of the errors will be here. Definitely not here. Let's see. So false positive type 1 error, rejecting the null hypothesis when in fact the null hypothesis is true. Find the defendant guilty when in fact defendant was innocent. Those are false error. False negative. Find the defendant not guilty when in fact defendant did commit the crime. That's false negative type 2 error. Failing to reject the null hypothesis when in fact the null hypothesis is false. Find the defendant not guilty when in fact they were innocent. Because the defendant was found not guilty when in fact they were innocent. Rejecting the null hypothesis when in fact the null hypothesis is false. There are two ways to get the right decision and two different ways to you can make the wrong decision. Okay, so we're going to refresh on that later. Voila. So we've completed the chapter 1, which is hypothesis testing fundamentals. So I'm going to two-step sample and ANOVA tests on day 76. So let's stop here for today. Alright, so that'll be the end of this hypothesis introductions to hypothesis testing in Python. So do make sure to download the dataset and practice your hypothesis skills in the description below. I'll see you on the next slide, which is the 76, as we complete this hypothesis testing in Python for now. Cheers, bye.